So, lots of reactions occur very slowly, but what we often want to do is make them happen a lot faster. Maybe we want to make more money by, producing more of a product, or we're just not very patient. So how can we increase the rate of a reaction? Well, reactions occur when reactant particles collide with a sufficient amount of energy. So the reactant particles have to collide and they have to break what we call the activation energy barrier. They have to collide with an energy greater than the activation energy for that reaction. And so obviously if we're mixing two reactants together, then we've got millions and millions of our reactant particles roaming around. And those millions of particles are likely colliding lots and lots and lots. However, because for some reactions these reactions occur very slowly, this tells us that lots of collisions are unsuccessful. Lots of the collisions between our reactant particles are unsuccessful. Lots of them occur with energy less than the activation energy. And so that gives us two ways we can increase the rate of a reaction. The first way is that we can increase the number of collisions between our reactant particles. If we increase the number of collisions between our reactant particles, then we're going to get more successful reactions and thus a faster reaction rate. So if we increase the number of collisions, we'll get a faster rate of reaction. Now there are a few ways that we can do this. To do this, we can firstly increase the surface area of our reactants. So if we think about it, maybe we're reacting something with a liquid chemical. So maybe we're reacting a big solid chunk of metal with some sort of liquid. We're about to drop our big chunk of metal into this liquid here. Now slowly we know that this metal is going to dissolve into this liquid as the reaction occurs. However, if we increase the surface area of our metal, if we maybe grind our metal down into a powder rather than dropping a big block in, then our reaction will occur faster. Now why is that? Well, if we leave our metal as a big block like this, then collisions between reactant particles can only occur on the surface of the block. The only metal particles that can touch our liquid, our chemical here, are the ones on the outside, and thus they're the only ones that can react. And as the ones on the very outside react, they disappear, they fall off, they dissolve into the chemical, into the liquid, and thus the ones slightly inside the surface can then collide with our liquid particles. However, if we chop this up into a very fine powder, then there's lots more surface area, and so there are a lot more collisions between our metal particles and our liquid particles, and so the reaction will occur at a much faster rate. So increasing the surface area increases the number of collisions between our reactants. Another way for us to increase the number of collisions is to increase concentration, or the pressure, if we're talking about a gas, of our reactant. So again, this increases the number of collisions, but how? Well, if we increase the concentration of our reactants, then if we're mixing two solutions together, in a beaker, so if we've got our beaker here, and we've got a solution, and we've mixed our two solutions together, so one solution contains these yellow particles that we can't obviously see because they're dissolved, but we're just drawing them here so we can understand the process, and these red particles. Now if we increase the concentration of these reactant particles, if we have a lot more of these red dots around if we have a lot more of these yellow dots around, then we can see quite visually that we're going to see a lot more colliding between the red and the yellow particles. And so that'll increase the number of collisions, and thus it will increase the rate of reaction as these two solutions mix. So obviously, if we're looking at gases as well, then increasing the pressure means we're going to have a higher density or a higher number of reactant particles in a given volume, and that's going to cause a lot more, it's going to be a lot more busy, there's going to be a lot more traffic, and so we're going to see a lot more collisions between reactant particles. Another way we can increase the number of collisions is by increasing the temperature of our reactants. Now what this does is, this relies on the fact that temperature is in fact a measure of kinetic energy. And kinetic energy is basically the speed with which a measure of the speed with which a particle is moving, or the energy of a particle due to its movement. So if we increase the temperature of our reactants, then that means our reactant particles are, on average, moving around a lot faster. If they're moving around a lot faster, then they're going to, again, run into other reactant particles more frequently. So increasing the temperature of reactants also increases the number of collisions between reactant particles. Now, another way, besides increasing the number of collisions, a second way that we can increase a reaction rate is, because lots of collisions are unsuccessful, is we can increase the proportion of collisions that are successful then we'll get a faster rate of reaction. Again, so if we can increase the proportion of collisions that are successful, if we can increase the proportion of collisions that occur with an energy greater than the activation energy, then we will get a faster rate of reaction. So again, if we increase the temperature, this will also increase this proportion. So if we increase the temperature of our reactants, then what this means is that, firstly, this relies on the fact that, again, temperature is a measure of kinetic energy. So if this is the number of particles, and this is the kinetic energy, or EK, then the temperature is in fact a measure of the average kinetic energy of particles. So if we have a graph of this for perhaps a sample of a reactant at 20 degrees, then it's going to look something like this. So we're going to have some, even if we're dealing with 20 degrees Celsius, then we're still going to have some particles that have very, very, very high kinetic energy. And we're also going to have some that have close to no kinetic energy. And we're going to have most of our particles with a kinetic energy around here. Now, if we heat this reactant up to, say, 30 degrees, then our graph changes to look like this. And so our peak is slightly further up. Our peak is at a slightly higher kinetic energy. However, the key point is this means that more of our particles have an energy above the activation energy. So if our activation energy is here, then that means at 20 degrees, all of the particles in here will be able to react, because all of these particles have energy greater than the activation energy. However, at 30 degrees, we've in fact got a bigger area. We've got a lot more particles with energy greater than the activation energy. And that means a lot more particles, or a larger proportion of particles, will be able to collide with energy greater than the activation energy. And that'll make a much higher proportion of collisions successful. So that's why temperature increases the proportion of collisions that are successful. Now, the last way we can increase this proportion is by adding a catalyst. And basically what a catalyst does is, a catalyst, interestingly enough, so catalyst, this reduces the activation energy of a reaction. So a catalyst, what it does, if we've got these yellow particles here reacting with our blue particles here, then if we add in a catalyst like this, then what happens is that these yellow and blue particles adsorb to the surface of our green catalyst. That means they just stick to the outside like this. And when they stick to the outside, because of this attraction for the outside of our catalyst, the bonds in these reactant particles are slightly distorted, they're slightly weakened. And what that means is it takes less energy to then break the bonds which are already weakened. And so this catalyst weakens the bonds slightly, and thus makes it easier, or makes for the bonds in particles to break. It means it takes less energy to break those bonds. And so again, by lowering the activation energy, we increase the proportion of collisions that are successful. So increasing reaction rates is all about increasing the number of successful collisions and increasing the proportion of collisions that are successful. So if we leave the number of collisions the same and we increase the proportion of collisions that are successful, then we're going to get more successful collisions. However, on the other hand, we're going to get a higher number of collisions which are successful. We're going to get a higher number of successful collisions. However, if we leave the proportion of collisions that are successful, if we leave that unchanged and we simply increase the number of collisions, then we're still going to get more successful collisions. And so increasing the reaction rate is all about finding a way to get more successful collisions taking place. And these are the two ways that we can do that. We can increase the number of collisions, or we can increase the proportion of collisions that are successful. And both of these aim to allow more successful collisions to occur. So if we want to look a bit further at this idea of a catalyst, we're going to take a generic. So we're going to leave that there. Adding a catalyst reduces the activation energy. And so what we're going to do is we're going to look at an example of an exothermic reaction, just a generic exothermic reaction, maybe a combustion reaction, maybe the combustion of some petrol. We're going to look at a generic exothermic reaction, and we're going to draw an energy profile with a catalyst and without a catalyst. So firstly, we'll draw it without a catalyst. So we know that the reaction is exothermic. So this is energy on this axis. This isn't really time, this is simply the reactants versus the products. So you could kind of refer to the horizontal axis as the stage of the reaction that we're up to. First of all, without a catalyst, it's an exothermic reaction. So we're going to have this abstract energy, or this abstract enthalpy of our reactants. We're going to have this activation energy process where the bonds are broken and energy is released as new bonds are formed, and it's exothermic, so the energy of our product is less than the energy of our reactants. And so we know that the difference between the top of this peak and the height of our reactants is the activation energy. And so a catalyst reduces the activation energy of a reaction. However, it leaves unchanged the energy of our reactants and the energy of our product. So that means we're still going to have a line there, and we're still going to have a line there. However, because our activation energy is less, the peak is going to be lower. And so if we add a catalyst to a reaction, it changes the energy profile like this. The only thing that changes is the height of this transition period of the reaction. It changes the height of this activation energy point. And so we've got a much lower peak on the activation energy part of our energy profile, and that is due to the addition of a catalyst. So those are the ways we can increase reaction rates, and they're the reasons that they're sort of the ideas that increase reaction rates and the practical methods that do so. So this is how specifically the effects of a catalyst manifest themselves in terms of an energy profile.